In this first AP problem, we have a bottle filling machine that we are working with, and we're going to eventually perform a test on this. It says the bottle filling machine is set to dispense 12.1 fluid ounces into juice bottles. We're going to circle that right away. To ensure that the machine is filling accurately, every hour a worker randomly selects 4 bottles filled by the machine during the past hour and measures the contents. There is convincing evidence that the mean amount of the juice dispensed is different than 12.1 ounces, and different, we'll underline that too, that could be important. Or if there is convincing evidence that the standard deviation is greater than 0.05 ounce, the machine is shut down for recalibration. It can be assumed that the amount of juice that is dispensed into bottles is normally distributed, and that as an underlying assumption could be important too. During 1 hour, the mean number of fluid ounces of 4 randomly selected bottles was 12.05, and the standard deviation was 0.085 ounces. Now the first thing says, perform a test of significance to determine whether the mean amount of juice dispensed is different than the 12.1 fluid ounces, and assume the conditions for inference are met. Now that line that says assume the conditions are met is going to make our test a little bit easier to actually do, because then we don't have to go through demonstrating that we have good information. Whenever you're going to do a hypothesis test, the very first step you want to do is define what your variables are. And it says that we are measuring a mean amount. So what we want to do is define what mu really represents. So mu is represented by the mean, and you might want to say population mean, because mu represents the population, and it's of how full the bottles are. So maybe number of ounces of juice. And then we need to go into actually defining what our null and alternative hypothesis is. Since we're dealing with the mean, we're dealing with mu. We already decided that. And what is mu going to be equal to? It wants to see if we are different from this 12.1 fluid ounces here. So if we are different than that, our null is going to be that mu is actually equal to 12.1. And because we're talking about a difference, and we talked about that up here too, different, it's not greater or less than, we're going to say mu is not equal to as our alternative hypothesis. So if we write this out here, our null, we always want to write null hypothesis or H0 like that, we would say that mu is equal to 12.1 ounces. And then our alternative hypothesis, we could write that out or say HA, is that mu is not equal to 12.1 ounces. We also want to pick a critical value, so we might decide that alpha is going to equal 0.05. That's just the standard unless there's a reason to choose something else. So now we have a null, an alternative, and an alpha value, and we know that mu represents the population mean number of ounces of juice in these containers. And now we need to actually carry out the test. First thing we need to decide is what test are we doing? Whenever you test a single mean and the standard deviation that you have from a random sample is given, and it says right here specifically that the standard deviation is from the 4 randomly selected bottles, that's when you're going to do a t-test. So in the same way with confidence intervals, you do a t-interval when you do not know the population standard deviation. With the hypothesis, you do a t-test when you do not know the population standard deviation. So let's zoom on in here. And we need to state when we're doing a test what test we're doing first of all. So we are doing a t-test. And we need to calculate our critical value of t. Or, well, in this case, since we can do that in our calculator, we're going to say what our t-statistic is and what our p-value is. from our calculator. The thing that we do in our calculator is we push the stat key, we go over to tests, and we choose t-test. It's going to be the second one down on the list, and I apologize for not having it up on the screen. And from there, you're going to type in a few pieces of information. The first thing it's going to want is to know that you are using statistics, not raw data. So you're just going to choose stats, and that will allow you to enter in all of your information. Your null hypothesis, mu0 or mu naught, is 12.1. That's what we had stated right here. So that 12.1 is our null. And then our x bar, x bar referring to the sample mean, is going to be the 12.05 that it talks about here. It says the 4 randomly selected bottles had a sample mean of 12.05. And then Sx, the standard deviation, the sample standard deviation is this 0.085 ounces right here. How many are sample sizes? What n is going to be this 4 bottles, because it says there's 4 bottles in a sample. And then when it asks you that mu is greater than, less than, or not equal to, we said our alternative hypothesis is that mu is not equal to. So we're going to select that, and we can go down then to the bottom and calculate. And when we calculate that, that's where we're going to get our t-statistic and our p-value. So let's zoom back in here, and when we get this out of our calculator, the t-statistic says it is negative 1.18 if we round it up, negative 1.18. And the p-value is 0.324. Once we have our values here, we can come to our conclusion. With a p-value so high, much higher than 0.05, our standard alpha value, we are going to fail to reject. So we want to say we fail to reject, and we can actually write that out. We fail to reject because our p-value is so much greater than alpha. And then we have to state what that conclusion actually means in context here. So in this case, we say we do not have the evidence, we cannot claim that the amount of juice has changed. So we cannot claim that the average amount of juice has changed. So we can write that out right there. And that's it. So you've gone through a full hypothesis test here. Now remember, there are some problems out there that will require you to state all of your conditions ahead of time, but fortunately this is not one of them. So let's scroll down to the second part. To determine whether this sample of 4 bottles provides convincing evidence that the standard deviation of the amount of juice dispensed is greater than 0.05 ounces, a simulation study was performed. Now a simulation study, that's basically them using something very similar to StatKey, and StatKey actually can do this for standard deviations if you ever wanted to. But nonetheless, in the simulation study, 300 samples, each of size 4 again, were randomly generated from a normal population with a mean of 2.1 and a standard deviation of 0.5. This sentence you might want to read a second time. In the simulation study, 300 samples, each of size 4, were randomly generated from a normal population with a certain mean and a certain standard deviation. That means that they actually had a normal distribution that they started with, and they randomly picked values out of that, and they'd pick 4 at a time, average them together, but look at what their standard deviation was as they did that. So they took the 4 values, found the standard deviation, and put a dot somewhere on this graph. And so the standard deviations of the sets of 4 that they drew are plotted out here, and this is what the graph looks like. The dot plot below displays the values of the sample standard deviations. So it says, use the results of the simulation studies to explain why you think the sample provides or does not provide evidence that the standard deviation of the juice dispense exceeds 0.05 fluid ounce. Now, 0.05 fluid ounce on here, be right here. It's right in the middle. And we want to see if there's evidence to say that it exceeds that. But more importantly, we want to look at the value that we actually got. So more important than that right there, we'll just erase that, is going back up and looking at our sample data is 0.085. And let's see where 0.085 falls. Somewhere around here. So it says there are 300 samples in the simulation. And if we look at how many are above that, we've got 1, 2, 3, 4, 5, 5 more, 2 more. So there's 12 up here, leaving us 288 over here, which means there's a 4% chance, if we take the fraction 12 out of 300, a 0.04 probability of ending up there. Now going back to our question here, it says use the results of the simulation to explain why you think the sample provides or does not provide evidence that the standard deviation of the juice dispense exceeds 0.05 fluid ounces. Now we looked at where the sample data that we got was, assuming that this null is true, and it only happened 12 out of 300 times, which is about 4%, a p-value of about 0.04. That means it's unlikely enough. When we assume alpha being 0.05, 0.04 is less than that. It does provide evidence that the standard deviation is too high. And so we are going to try to now as a conclusion. First thing we're going to say is that assuming alpha is 0.05, if the null hypothesis is true, which in this case, if the standard deviation is truly equal to 0.05, and the reason I use sigma here and not s is because I'm referring to the population. We're assuming something about the population, just like we assume a null hypothesis of mu equal to something. Since we're talking about standard deviation, you say a null hypothesis of sigma equal to something. If sigma is really equal to 0.05, there is 0.04 probability of finding a sample standard deviation, finding S, and I always use that little X down there to refer to the original population, of finding S greater than the data that we found, which would be 0.085. So there's that probability of finding that. Therefore, there is enough evidence to reject the null. Enough evidence to reject the null. The juice machine does have a standard deviation above 0.05. And you'd want to write all of these things out. And what that does is that tells you that you have a pretty good, clear explanation of the whole process.